Hi there, this is Archie Moores for the Mass Spring PID controller coursework. So to start with, I have created a system which can be seen here, which is a system with a mass spring plant with a PID controller and a sensor over here. It has a sine input with an amplitude of 1, as seen here, with a frequency of 1 as well. So for the mass spring plant, I have to start off with a mass over here with a mass of 2, and that then feeds into a series of integrators for the mass spring system to get velocity and displacement, with damping labelled here as 1, along with the spring constant here labelled with a value of 2. And both of these values both feed back into this system in order to create a feedback loop, so this system is a continuous system. Along with that, the output of the mass spring system feeds back, along with its error, feeds back in through with the sine wave input into the PID controller, so it can measure its error and compensate for that, which then in turn feeds back into the mass spring system, eventually giving an output for this scope over here in order to show what the system eventually outputs. So I've started off with the PID with the basic values that have been set with the software. So I'm just going to click on this and just show you that the proportional value is 1, integral value is 1, and the derivative is 0 with a constant of 250. So we're just going to run this program to see the graph that it gets, and then it can be shown here. Now, as you can see, that it's got a slow reaction time and quite a high overshoot. Its settling time also is not great. I've also set the time to 60 seconds, and as you can see, it hasn't settled within the 60 seconds. It's got it hasn't got a great steady state error, as all these peaks are shown to be they don't have a very good continuous nature to them. They have quite a lot of error within those peaks, and there's quite a lot of inconsistency. So in order to combat this, especially the rise time, I'm now going to increase the proportional value and the integral value to 10, and also the derivative value to 5. So I'm just going to apply that now, and then we will run the simulation again. And as shown, the rise time is much quicker, but there is still some significant overshoot on the peaks. But the steady state error is looking better. The rise time is better. The overshoot is still significant though. The set time isn't looking too bad. The steady state error is not as good, because that is the result of increasing both P and I. So in order to combat this, I'm going to reduce all the variables to P. I'm going to change to 5 again, and the same with the integral. And I'm also going to decrease the derivative to around 2 to see if that has any difference. So you're going to run that again and see what happens. So there is again an overshoot, but it is less. But again, these peaks are still not settling properly, so that has to be corrected. The steady state error is looking better. There's a better, there's more of a straight line across here, which shows an improvement. The stability is looking better. The steady state error again is good, but obviously can be improved. So I'm going to further tune this. I'm happy with the proportionality, but I feel that the integral could be decreased in order to combat this overshoot here, and so it settles faster into its pattern. The derivative could be a bit higher as well in order to help settle it. So I'm now again going to change these settings on the PID controller. So proportional is going to stay the same, but derivative is now going to increase to 3, and then the integral is going to decrease to 2.5. So we'll apply that again, click OK, and then run this one more time. And as you can see, rise time is good, steady state error is good, it's settled in quickly, and the steady state error is also looking good. It doesn't really change much, and it's hitting all the correct values of 1 and -1. The periodicity is correct as well, with periods of pi/2. So I now believe that this PID is tuned, and this is the best. These are the best values for it to create the most steady system that gets to its target as quick as possible, while also maintaining a good level of stability with little overshoot.